Hello, good morning, students. Welcome back to the second class of the chemistry. Now, first of all, I just want to ask that any doubt in yesterday's topic, just let me know. If there is no doubt, then we can proceed for the next topic. Just waiting for the questions to be asked by you.
Not yet, no idea.
No doubts at all. So just I'll take the 1 minute to explain the previous topic so that we can correlate the yesterday topics with the previous topic. Now the first one. Okay, Satya, good morning. Okay, Yash Mota, good morning. Fine. I'm just asking you any doubt in the yesterday's topic so that we can proceed for the next one. Or rather, you just sending the good morning, you can ask the question later. Okay, fine. No doubt at all. Okay, clear, student. Okay, yesterday we have discussed the type of the solutions. The one was ideal solution and the second was a non-ideal solution. And we described the postulates of the non-ideal solution. The first one was those which follow the Raoult's law. Second was that the force of interaction will be same before solution making and after solution is produced. Now third one was that delta V was 0 and delta H was enthalpy was 0. So these were the four assumptions for the ideal solution. And on the contrary, you will see that those which do not follow all those four assumptions, these are called non-ideal solution. So now today we will start that same topic, that non-ideal solution, and we will proceed with the various type of the solutions. Okay. So first, now we have discussed that the topic was non-ideal solution. Okay. So we have seen that non-ideal solutions are those solutions in which when the solute and the solvent are mixed together, there will be a change in the volume. They do not obey the Raoult's law. Delta V will be varied and delta H will also be different. Is it force of interaction will be different? Is it fine? So we will take that force of interaction again, and we will think about that. What happens when the force of interaction will be either increased between the solute and the solvent, or what happens when it is decreased in the when the solution is prepared by mixing of the solute and the solvent. So let's start with that. Yesterday we have taken one example. Suppose there is a solvent which is of A type, and you will see that this is the A type of the solution. We are taking an example. The molecules are present in they all are also due to the AA type. Now, the force of interaction present between the A will be the AA type. Is it fine? Because this is a homogeneous and same molecules are present in the solvent. Now, on to the second one. Here, you will see this is the solute, which is also in the liquid form. Is it fine? Now, you take that second B. Fine. The molecules present in that will also be of B type. Okay, and the force of interaction present between that will be B type. So this will be the solvent and this is the solute. Is it fine? Now, what will happen when we mix them together? The new force of interaction generated, and that will be what? AB type. Is it fine? So in the previous lecture, I explained that the force of interaction between the AB, if it is equal to AA or BB, then it is called as an ideal solution, and if the force of interaction is different from AA or BB, then it is called as a non-ideal solution. So my topic for today is non-ideal solution because of the force of interaction will be different. I hope you understood this thing. Now, the next thing is that if you talk about the force of interaction between A and B, if it is greater than AA and BB, then what will happen to the vapor pressure? Or if the force of interaction between the AB is weaker as compared to the AA and BB, then what happens? Is it fine? So we will discuss that these are the two different, phenomena. These are the two different force of interaction, and what will happen to the vapor pressure when the different bonds or different interactions are there. So let's discuss first thing. If we talk about suppose AB force is greater than either A interaction or B interaction. Is it fine? The first example is that the A-B force of interaction is stronger. Is it fine as compared to the solvent interaction as well as the solute interaction? Is it fine? What will happen in this case? You will see that if the force of interaction is stronger, then what happened? The solute particle will not allow the solvent particles to form the vapors. Is it fine? Not allow means they will allow. But if you compare the pure solvent, is it fine? If you compare the solution, then what happens if the force of interaction is stronger? Then what will happen? The vapor pressure will be decreased because the force of interaction is stronger. So what happens? This particle will not allow this particle to move outside to form the vapor. Is it fine? So this force of interaction is generated because of either hydrogen bond or any van der Waals forces which can be present in that. Did you understand this part? So ultimately we can say that if force of interaction between AB is a solution, if it is stronger than the solvent or the solute, then what happens? The vapor pressure of the solution will decrease because of the stronger force of interaction. Did you understand? So the vapor produced will be also less. Is it fine? So if at a particular temperature vapors so produced which are very less, then what will happen to the Raoult's law graph? So yesterday I made one graph here. So this is the graph, and yesterday I have taken x1 was 1 and x2 is equal to 0, and here x1 was equal to 0 and x2 is equal to 1. Okay, this was mole fraction and amplitude, and that vapor pressure here, and that is also vapor pressure. Is it fine? And if you take this one P1 naught, that was the vapor pressure of the pure solvent, or this is the P2 naught, that was the vapor pressure of the pure solute, which will be taken in liquid form. Now what we did, we combined them. We joined them. Is it fine? And we obtained such type of the graph. Yesterday I have explained this thing, and this was the P2 was equal to P1 naught x2. P2 naught x2, and this will become P1 is equal to P1 naught x1, and this was the P total. P total is what? That is equal to P1 plus P2. This was the graph we already discussed in the regular class and even yesterday also. Is it fine? Now we have to describe this thing on that. So my question was, what happens when the force of interaction between the solute and the solvent will be stronger as compared to the solvent and the solute? Is it fine? So I told you that, I explained that, but if the force of interaction is stronger, in that case, either B or A will not allow any of the particles to move up. Is it fine? The rate of the evaporation will be lesser. The vapor pressure will also be very less. Is it fine? So if the vapor pressure will be very less at a particular temperature, then what will happen? Then you will see that there will be a deviation in the Raoult's law graph, and this deviation will be negative deviation. Is it fine? This is called as a negative deviation. What is the meaning of the negative deviation? See, the graph was like this. The graph was like this. Is it fine? And if the vapor pressure will be less, then what happens? The graph will be moving down. Is it fine? So what happened? If you will obtain a parabola kind of the structure, is it fine? It shows that the yellow line which I have made later on, this decides the lowered vapor pressure. Is it fine? So we can say that if the force of interaction between A and B is stronger as compared to the solute and the solvent interaction, then what happens? The vapor pressure will be less, and it will show the negative deviation in the Raoult's law graph. I hope all are clear with that. So this is the first part. Now come to the second one. What will happen if the force of interaction between the A and B is lesser than AA and or BE? Is it fine? So this is the second condition. What will happen when the force of interaction between A and B is lesser as compared to the AA force of interaction or BB force of interaction? In that case, just opposite to one. Whatever, if the force of interaction is less, the at a particular temperature, particles will get free much easier, and if the particles will be separated easily, then they will evaporate much easily. Is it fine? And they will form the large vapors. That means vapor pressure will be increased. Understood this thing? If the vapor pressure will increase, then what will happen to the Raoult's law graph? So in the previous case, you have seen that there was a negative deviation in the Raoult's law graph, but in the second case, if the force of interaction is weaker as compared to that one, then the particles will get separated much easier and they can form the vapors, and these vapors will be larger at a particular temperature if you compare with the pure solvent or the solute. So in that case, you'll see that there will be a positive deviation in the Raoult's law graph. There will be a positive deviation in the Raoult's law graph. What type of the positive deviation? So just listen. Fine. So this was P1 naught and this was a P2 naught. If you join this graph this side, if this graph is joined and you talk about this thing, so this was the same thing. This was a P2 and this was a P1 and that was a P2. Is it fine? That one x1 is equal to 1 and x2 is equal to 0. If x1 is equal to 0 and x2 is equal to 1. Is it fine? So I told you that here there is a depression in the Raoult's law graph. That means that is a negative deviation because the less vapors are produced at a particular temperature. If you want to increase the vapor pressure, then you need to increase the temperature. But we need to keep the temperature constant. At the particular temperature, vapor pressure will be low. Is it fine? But here in this case, you will see that the vapor pressure at a particular temperature will be larger or more as compared to the AA and BB. Is it fine? So there will be a positive deviation in that, and this graph will look upside down. Is it clear, students? So this will show the positive deviation in the Raoult's law graph. So this is negative deviation. Why is it so? Because the force of interaction is stronger as compared to the solute and the solvent. So there is a negative deviation, and here you will see the force of interaction is weaker as compared to the solvent and the solute. Then there will be a positive deviation. Is it fine? So these are the two type of the interaction which can be produced in the non-ideal solution. And what type of the force of interaction will be there? It may be the weak hydrogen bond or stronger hydrogen bond or van der Waals forces. Is it fine? So these are the few interactions which are generated when you make the solution. Is it fine? Now, any question into this part? Otherwise, we'll take the next topic, that is azeotrops. Yeah, Manchapar. Yesterday you said that in the case of ideal solution, the initial volume is 1 liter, but the initial volume would be 2 liter. Both the solution were taken 1 liter. Yeah, exactly. See, yesterday I told you that we have to take one solvent and another solute. Is it fine? Both are in the liquid form. Like taking an example, N-heptane and hexane. N-heptane is 1 liter. N-heptane is also 1 liter. Is it fine? So individually 1 liter is there. Is it fine? Now we combine them together. Then according to the rule, whatever, according to the non-ideality, whatever, it should be 2 liter. But they are making only 1 liter. So 1 liter solution that will be equal to 1 liter of what? Your either solute or the solvent. So I explained it that way. So 1 liter of the solute, 1 liter of the solvent. So one individually, and when we mix them together, the answer will be again 1 liter. It should be 2 liter, but it is 1 liter. Is it fine? So that is why this is called ideal solution. I told you that 100% ideality is not possible. So we try to make them towards the ideality. Is it fine? We try to bring them towards ideality. Is it fine? So this was the yesterday's topic. Is it clear? So I hope one doubt has been clear. Sir, what are what is that? What is the meaning of that? This strictly restricted non-ideal solution. What is the meaning of that, Sanskruti? I didn't understand your question. Sanskruti just asked. Just ask the question. No question at all. Okay, fine. Just let me know. This is a non-ideal solution. Ideal means what? The force of interaction and everything is same. Yesterday you were not there, I think so, in the lecture. That's why. So just see that in the ideal solution, what happened? The force of interaction was same. Raoult's law followed. Is it fine? And the third thing is that delta V will be 0 and delta H will also be 0. Everything was there. I explained yesterday. And this is the non-ideal, and I have taken that on the basis of the force of. Yesterday, ideal solution, force of interaction was same. But here I have explained that force of interaction is different in the non-ideal. So ideal and non-ideal both are different, Sanskruti. Is it fine? So this is the description of the particular non-ideal solution. I hope you understood this thing. Now the next thing comes, that will be the azeotrophs. Do you know what is the azeotroph? What are the meaning of the azeotrophs? Anyone? Yeah, this is a concept which is related to the non-ideal solution. Yes, of course, it is related to the non-ideal solution, not the ideal solution. Because ideal solution, according to rule, they all are having the same force of interaction in everything. Is it clear? Fine. So, Sanskruti, I hope your doubt is clear. Yes, you have written the same. Now come to the next part, azeotrophs. You know that before starting this azeotroph topic, I just want to ask you, like, if I give you a mixture of a solution of water and alcohol, fine. So water will be taken as a solvent and alcohol will be taken as a solute. Is it fine? When both are mixed together, clear? So the solution of the alcohol is produced. That is a dilute solution of the alcohol. I hope you understood this thing. Now, the question comes to you is, how will you separate them? How will you separate them? Like, after mixing of that, what is the procedure of the separation of these two components? So in the mind, only one thing comes, that is called as a distillation technique, or simply we can say fractional distillation technique. I hope you understand this thing. So in the fractional distillation, what happens? Only two components are there. The one is the water, and the second is the alcohol. So what you will do? The first procedure is to heat up the solution. So the solution will boil up, and after boiling, what happens? The alcohol will be evaporated very early, because the boiling point of the alcohol is quite lower than that of the water, and the water will be evaporated somewhat late. Is it fine? So these are the two conditions we can say. Is it fine? So first alcohol will be collected and later water will be collected. This could be the answer. But here, according to the distillation, we should say that the 100% of alcohol again obtained after distillation and 100% of water should be obtained after distillation. Is it fine? This is the criteria we follow in the distillation, but it is not true, I tell you. Because that is called as a constant boiling mixture. When you boil them together, then what happens? The alcohol which will be obtained in the fractional distillating column, that will be 95% pure, and 5% water will be added in that and be considered as a rectified spirit. Are you getting it? That means at this point, it is not possible for us to separate both the components 100%. So these constant boiling mixtures are called as azeotrophs, and this is the binary azeotroph. Binary means what? One is alcohol and second is water. Both are mixed together. Now we have to separate them, and before separation we need to heat this solution. So alcohol will be separated and water will be separated. Is it fine? But if you talk about the percentage of the purity of the alcohol, then it will be only 95%. 5% what is that? That is called constant boiling mixture, or it is called as azeotrophs. So now condition is that if 95% alcohol is there, but in the laboratory we are using the 100% alcohol, then how will you get this 100% alcohol? And it is a binary solution. And how will you obtain this? How will you obtain this alcohol as a 100%? Then the thing comes that we need to add a certain amount of the benzene in that. So there are the trinary azeotrophs. The first one is water, second one is alcohol, and third one is benzene. When you add all these three, then what will happen? The same thing is that when you boil them together, at the top, what is obtained? Benzene, alcohol, and water. All the three will be obtained. I will just explain on the board. Just listen it. Man, yes, you are right. Azeotrophs are constant boiling mixtures. Absolutely right. Fine. So I have taken one example: water and alcohol. This is the mixture, and we have to separate it by the fractional distillation. This is to be separated by the fractional distillation. And I told you that when you take this column, this is the fractional distillating column, Suppose two columns are there in that, or maybe three columns may be there. Is it fine? So if you take these two only, is it fine? Then what will happen? Both will be vaporized. Fine. So here you will see that alcohol will be obtained, and here water will be obtained. Fine. So we expected that alcohol should be 100% pure. Fine. But I told you that this is the 95% and plus 5% of the water is there in it. Is it fine? So that means both are boiled together and both will get separated by the 95 is to 5% purity. Is it fine? That means at this, although what happens when you boil them together, is it fine? So that should be 100% alcohol and here water should be 100%. Is it then 100% purity should be there? But here in this case you will see that because of the hydrogen bond, what will happen? The alcohol and water will not get separated at the particular temperature. Is it fine? So at the particular temperature, alcohol will be 95% pure, and this is called as a the water will be the 5% pure. 5% combination. This is called rectified spirited. Did you understand this part? But we need to separate this mixture, and we have to get the 100% alcohol. For this, what we need to do? So this is, I told you, this is the binary. Binary is your drop. Now, to separate this alcohol from the water, what we need to do? Water plus alcohol or plus benzene. It may not be there in the textbook. Is it fine? So water, alcohol, and benzene. These are the three components which are mixed together. Is it fine? And this is called as a trinary. Okay. Trinary azeotrope. So I hope you understood this thing. So how this combination will be separated? दो separate हो नहीं रहे थे और आपने तीसरा मिक्स कर दिया, थर्ड कर दिया, तो फिर ऐसे कैसे काम चलेगा? फाइन. तो दो हो नहीं रहे थे, थर्ड वाला क्या काम कर रहा है? थर्ड वाला क्या चीज कर रहा है? तो वो देखते हैं इसके अंदर. So I just want to explain. If it is a fractional distillation column, is it fine? Okay. So the first part will be there here. ये यहाँ से vapors आएंगी. These are the vapors which are initiated from there. This is, I'm talking about this combination: water, alcohol, and benzene. All will get evaporated. At the low temperature, you will see that water will be there, plus alcohol will be there. Okay, and plus benzene will be there. Okay, all the three vapors will be collected here. Clear? Now, in the second case, you will see that water plus alcohol. Understood? The combination will be different. See, the percentage combination will be different. Is when water can be 65%, it can be 12 point something percent, rest may be the benzene. Here water could be the 75%, alcohol can be another thing. Is it right? But here you will obtain the 100% pure alcohol. Understood this thing? So after the combination of benzene, what benzene did? What was the use of the benzene? The benzene has decreased the force of attraction between the water and the alcohol, and it made the new force of attraction between the water as well as with the alcohol. Is it fine? So all the three components have different interaction, and due to this interaction, what happened? The different fractionating columns are there and different combinations are there. So at low temperature, water, alcohol, and benzene will be separated. Now here water and alcohol will be separated, and in the third one, 100% pure. Alcohol will be separated. Although the quantity of the alcohol will be less, is it fine? But still, the question was that how will you obtain the 100% alcohol from this combination? Did you understand this part? So this is called as a constant boiling mixture or the azeotropic. Yeah, azeotropic mixture. I hope you understood this thing. Any doubt in this case? And we will classify the azeotropes into two parts later. But just let me know any doubt in that. The benzene will go at the first part. Whole benzene will go at the top level, at the lower temperature. Fine. And the second thing is that only benzene need to be used. Yeah, benzene. It's an example, beta. It's a different. There are many combinations. You can use the dichloro, methane. Is it fine for the other? So different azeotropic mixtures are having the different combinations. Is it fine? This is one example, because in the laboratory we are using 100% alcohol. So by normal fractional distillation, it is not possible for us to obtain the 100% alcohol because it is 95%. 95% is to 5% combination is there, and they boil at the constant temperature. So we need to separate and we have to get the 100%. That's why this one example I have given. There are many examples. You can explain many things. You can see many things, but this is one example which will be used in day-to-day part. Is it fine? So, sir, but left benzene heavier. No, beta, it's not. We are not talking about the heavier or the lighter. We are talking about the boiling temperature, beta, and the force of interaction. Believe if the weight is heavy, is it right? If the material will be having the weight, high weight, but still it can boil at the lower temperature. Is it right? So heaviness and the lightness does not work at all. Is it fine? So this is not the relevant thing. Is it fine? Rigved, I think your doubt is clear. So we will not discuss anything about the heavier part because heavier does not, it's a force of interaction, beta, whether it is heavy or lighter. Are you getting me? So don't separate on the basis of the heaviness or the lightness. Did you understand? So ultimately we came to know that, see, is it also constant evaluation? Sir, what if the boiler resulted in 90? Yes, Rigved asked me one question earlier. Rigved is asking that, sir, what will happen after getting the 95% is to 5% of the alcohol? What will happen after we will boil them together? They will not separate it better. Suppose if I am taking 120 degrees Celsius and 120 degrees Celsius, both will get separated. Is it fine? Sorry, both will get separated, but the combination will be having 95% alcohol and 5% water. If you increase the temperature to 140 degrees Celsius or 150 degrees Celsius, then still the combination will be same. Are you getting me? They will get evaporated, totally converted into vapor form. Is it fine? And still the combination will be same. Is it fine? So that is the problem. Otherwise, is there any problem to increase the temperature? Without any adding of the benzene, if we increase the temperature and we are getting the 100% pure, then what is the use of doing all these things? Is it clear? So the question is, like, whenever you are increasing the temperature further when both are separated, there is no separation by 100%. That is why we need to add the third component in that, which will make them separate so that we can obtain the alcohol in the 100% purity. Is it fine? I hope Riku with that is clear to you. Saraswati. No, beta. No. Liquid is not there. We will cool it and again see after cooling the combination will be there. The combination same will be there. And then again you will heat them because the force of interaction which is there, which will be constant, whether it is in vapor form or in the liquid form. So there will be no use of just cooling it down and again boiling it down, again cooling it down. This will be the cumbersome process. Is it fine? Why you are going on this kind of the process? Although, suppose if there is a variation of 0.1% or 2%, but we will not obtain the 100% by just doing this cumbersome process. Are you getting me? So, to overcome all these problems, is it fine? So, we have to add the benzene in the one task, in the one part. After adding the benzene, what they will get separated. And why separation is required? Because alcohol, this will be commercially used, and we follow those procedures which are cheaper to the company. It is cheaper for the whole, the alcohol makers. Are you getting me? So we do not do like this, just heating it up, cooling it down, then again heat it up and cooling it down. So what will be the variation? Only 0.1 or 0.2%. That's it. But water will be there. Is it fine? Because the hydrogen bond is stronger. Is it clear? So this is the thing. I hope so. Rigved is also satisfied with this, and any other? Only benzene need to be free. You guys answer. Okay, fine, students. So all doubts are clear to you. Yes. Okay. What is that? Murari Agarwal. Okay, beta. Done. So we will come on this part. The azeotrophs, we have seen that they boil at constant temperature in any case, any state. Is it fine? There can be two types of the azeotrophs. What is that? The first one is shall I write it down? How? It's 10:50. So let me finish this part. Okay, so we'll discuss that two type of azeotrophs. One is a maximum boiling azeotroph. I'm now writing full. And second will be the minimum boiling azeotroph. Is it that there are the two parts of that? The first one is the maximum boiling azeotrophs. What are the maximum boiling azeotrophs? Suppose if you talk about that any azeotroph you will make by this one, A or B combination. One will be the solvent and the second will be the solute. So if the force of interaction between A and B is stronger, is it fine? So it requires more temperature to get evaporated. Understood this thing? It requires more temperature to get evaporated. So here maximum is what? The boiling point will be increased. So boiling point after increasing the boiling point, what happens? It will reach to that pure level. Is it fine? So what are the maximum boiling azeotrophs? The azeotrophs in which the azeotropic solution in which the force of interaction is stronger. So they require high temperature to get boiled. Is it fine? And at a particular temperature, they will form the low vapor. So they will also show the negative deviation in the Raoult's law. Is it fine? It will be similar. It is a kind of non-ideal solution, but it is another category actually. Is it fine? So ultimately we can say that the maximum boiling azeotrophs are those azeotrophs in which the force of interaction is high, and due to which what happens, they require high temperature to get boiled and they will get separated at high temperature. Is it fine? And they will show the negative deviation in the Raoult's law. Okay, now the second one is coming, that is a minimum boiling azeotrophs. What is the meaning of azeotrophs? So here you will see that the force of interaction between A and B will be weaker as compared to the solute interaction as well as the solvent interaction. Is it fine? The same thing which I have already explained in the previous topic. Fine. So the force of interaction is weaker, but they will boil at the low. So I told you that they are constant boiling mixture. So boiling temperature either increase or boiling temperature either decrease. Is it fine? Suppose like water is boiled at 100 degrees Celsius. Is it fine? Or alcohol we can say suppose 90 degrees Celsius. Is it fine? So maximum will be the 100 degrees Celsius. So what is the meaning of the maximum boiling? So if you add alcohol in the water, the temperature will be increased from the 100 to 120. That means from the maximum that was 100, now it is increased to the 120. So this is why what happens? 100 degrees Celsius, at 100 degrees Celsius, the vapors will be produced and they will get separated. Did you understand this part? Okay, at 100 degrees Celsius, the vapors will be low, or their separation will be somewhat lesser. Is it fine? So that boiling temperature will be increased. Yeah, this is why that's why these are called as a maximum boiling azeotrophs. So at 100 degrees Celsius, their vapors will be low, so they will show the negative deviation in the Raoult's law. I hope you understood this thing. Suppose if the force of interaction between A and B is weaker, like we can take. Suppose any solvent or the solute, if the boiling temperature is 100, one is having 100 degrees Celsius boiling temperature and the second one is having the 90 degrees Celsius temperature. Is it fine? And they both are mixed together and the new force of interaction generated. Then when you boil them up, then what happened? The temperature decreased to the 90 degree. In the previous case, what happened? The temperature of the boiling was increased from 100 degrees Celsius to 120. But now the temperature of the separation will be decreased from the 90 degrees Celsius to the suppose 80 or 70. So at a lower temperature, they will boil. At a lower temperature, they will boil. So once they will boil at the lower temperature, that is why these are called the minimum boiling. Minimum is what? They have the minimum boiling temperature. So at the lower temperature, they will form the larger vapors. And what happens if you just see the vapors, that they will show the positive deviation in the Raoult's law. So I hope you all are understood with this topic, or it is clear to you. So azeotrophs is what? Suppose alcohol and water both are combined together. So we took that 100 degrees Celsius is the temperature at which they should boil, but now the boiling temperature increased by 120 degrees. So that will call you as the maximum. Is it fine? If you take acetone or any other thing, then what happened? They should boil at 90 degrees, but they boil at 80 degrees. That means from the lower temperature they have been decreased. Whatever the lower temperature was there, the boiling temperature has been decreased. Is this fine? So that's why these are called as a minimum boiling azeotrophs. Maximum boiling, lower vapor pressure, negative deviation in the Raoult's law, minimum boiling, positive deviation in the Raoult's law, and maximum vapors are produced. I hope you understood this. This is called as a azeotropic mixture and types of the azeotropic mixture. This is the last topic. Any question related to this one, please let me know. Okay, man. Thank you. Okay. So why is the maximum? No, 68% again. You are coming by mass, beta. I told you mass does not have any effect on that. Again, the same question you are repeating. Sometimes Ritu will ask, sometimes Jenny is asking. Fine. The mass and the weight does not create any effect. I told you that. The force of interaction, everywhere I'm just clarifying the one topic, the force of interaction which is responsible for all the data. Whether the maximum boiling, minimum boiling, positive deviation, negative deviation, ideality, non-ideality, is it fine? Gas, liquid mixture, liquid mixture, solid liquid mixtures, all these are based on the force of interaction produced by mixing of the solute and the solvent. So mass and this thing does not create any effect on that. Are you getting me? Mass will be responsible for just describing the mole fraction. The mole fraction is the quantity. Is it fine? The quantitatively, if you see that there will be change in the vapors and all these things. But here, what's that? It's nothing better. Okay? So why is the maximum temperature including and minimum temperature decreasing? Okay, fine. Okay, fine. I told you the data. The thing is that suppose now I have no other example. I have the two things with me. So one duster, yellow color, black color. Okay, this is the solvent and this is the solvent. Okay, now you understood maximum volume. I'll take a few more minutes now. Yeah. Okay, this is the first one. This is the solvent and this is the solvent. Okay, suppose I am taking that it boils at 100 degrees Celsius and it boils at 90 degrees Celsius. Okay, pure this yellow duster boils at 100 degrees Celsius and it will boil at the 90 degrees Celsius temperature. Okay, now I mix them together and I make the solution. Is it fine? Then the new force of interaction will be generated, beta. This force of interaction may be hydrogen bond or any van der Waals force. If the force of interaction is stronger, then what happens? It will be very tough for us to separate them. So for this purpose, if you give the temperature 90 degrees Celsius, then again they will not separate it because the force of interaction is stronger. And if you give the temperature of 100 degrees Celsius, then also they will not get separated from each other. So in that case, what will happen? We need to increase the temperature from the 100 degrees Celsius to any other temperature. Suppose 120 degrees Celsius, both will get separated and they will get evaporated. Are you getting? So from the maximum temperature, the temperature has been increased. Is it fine? So that is why it is called as a maximum volume. Which thing is responsible? Which force is responsible? I told you maybe the hydrogen bond. I hope you understood this thing. Now come to the second one. It is having the 90 degrees Celsius temperature and it was having the 100 degrees Celsius temperature. When we mix them together, I am talking of the second example, that minimum volume azeotrops. 90 degree, 100 degree. Okay. Combine them together and if I try to boil them up, then what happens? It should be boiled at a 90 degree, it should be boiled at 100 degrees Celsius, is it fine? But here what happens? What will happen? The temperature will be lowered from the 90 degree. At 80 degree, they will get boiled and they will get separated. Is it fine? So these are called at lower temperature, they will get boiled up. Understood this thing? So this is why this is called as a minimum boiling azeotrops. I hope you understood this thing. It is clear? So, Muranilal Agarwal, I think your doubt has been cleared. All azeotrops. Yeah, yes. Then Buddhu, what? All azeotrops are non-ideal solution. Okay, thanks a lot for today and we'll proceed for the next topic tomorrow. So let's read all these things and if you have any doubt, you just contact me on my WhatsApp number or you can call me up or you can just write your question and click the photograph and send it to me or you can ask tomorrow. Is it fine? Okay, thanks students. Bye for today.